vector, eigenvalue, especially eigenvalue when eigenvector is known, and power method to determine the biggest eigenvalue once a matrix is given. And as I mentioned before, the direction of finding eigenvalue from a vector isn't difficult. So the way is just making these numbers. Instead of vectors, we make numbers, then we can divide. With this form, we cannot directly divide, but with numbers, we can divide, right? Number by a number is possible. Number over a number is possible. So I mentioned it. The other direction is done by inverse iteration, which is nothing but the power method. Power method determines the biggest eigenvalue, and we can use the inverse iteration to determine the eigenvector from the value. So roughly, power method and inverse power method are identical. And I mentioned these things before. And if you have a question, ask me. If you don't, then I will continue.
Two ways to find eigenvalues. One is the method to use that row vector. The other method is the power method.
What do you mean by row vector? Or
The one you just showed us, we multiply R times the matrix and vector.
Oh, this is only when eigenvector is known. Only when eigenvector is known, then we can find the eigenvalue for the corresponding eigenvalue. But if we don't know the eigenvector, then what should we do? That's the next task. Any other questions? So this is the strategy. Matrix A is given, then we don't know what the eigenvalue or what eigenvector and eigenvalues are, right? We don't know these things at all once a matrix is given. But somehow assume that eigenvector is known, then this direction is easy, right? This direction is easy. Why? Because by the formula that I gave you, you can find eigenvalue. The difficulty direction is this one. It's not easy, right? It's not easy. So inverse power method is necessary. Of course, once we go to that area, I will cover the method. But inverse power method, inverse iteration method, right, will be used. But now, problem is deeper, because once A matrix is given, how can you find either V or lambda, anything? How can you find anything? That is the task. Fortunately, power method determines biggest eigenvector. So let's say eigenvector corresponding to the biggest eigenvalue, right? Power method determines biggest eigenvalue corresponding eigenvector, right? So power method determines biggest one, but it doesn't mean we know every eigenvalues and vectors. There are, for instance, 10 eigenvalues and vectors, but power method determines the biggest eigenvalue corresponding eigenvector, right? So the eigenvector corresponding to the biggest eigenvalue can be found, but what about 9 others? That is the situation. Any questions? Yes? Vector. Right. So I just call biggest eigenvector. What does that mean? It corresponds to biggest eigenvector. So power method only determines one eigenvalue among many, right? One eigenvector, in fact, right? One eigenvector among many. This eigenvector happens to be the vector corresponding to the biggest eigenvalue, magnitude-wise. It's complex, so it's magnitude. The magnitude-wise biggest thing is found. That means, what about 9 other eigenvectors and values? That is the situation. Do you have a clear picture? A matrix is given, then we want to find anything. But assume that somehow we know eigenvector, then eigenvalue can be found. somehow we know the eigenvalue, then you can find the eigenvector. So once one is known, the other is found, right? Once one is known, the other is found. So knowing eigenvalue and vector are identical in this sense. Then the next task is finding anything from A. The biggest can be found by power method. But what about others? This is the situation. So I introduced the way people deflate the matrix. So this is the situation. Once we have a matrix A, like this one, then we somehow extract the remainder after removing this portion. After removing this portion, we can extract this portion called B. So B is a smaller matrix. And then, once B is extracted, then we do the same thing to extract C, and so on, right? Then each time we get smaller and smaller matrices. Assume that two matrices are similar, and similar matrices are defined by this property. Once we have this situation, then we say P and Q are similar. When P and Q are similar, eigenvalues are the same. In other words, eigenvalue of P, eigenvalue of Q are the same. In other words, somehow, if we can achieve this thing by using similarity, so we use the notation like this. P and Q are similar. If P and Q are similar, then we share the eigenvalue. P and Q have the same eigenvalue. So what is the goal? We want to achieve this thing. Matrix A, right? Matrix A becomes this type of matrix. So I said equal, but it is in fact similar, right? So we find the matrix similar to this thing. And then once these are similar, eigenvalue of this one, and then eigenvalue of this one are the same. And then we want to find the eigenvalue of the outer part, and then we want to find the eigenvalue of B part. Then eigenvalue of B is the subgroup of subset of eigenvalue of A. In other words, eigenvalue A could be, for instance, lambda 1, lambda n. Then eigenvalue of B is nothing but something missing but lambda 1 through lambda n, and one eigenvalue among these things might be missing, right? One missing. Do you follow me? So once we have this similarity with this condition, then eigenvalue of A can be obtained by finding eigenvalues of B and eigenvalue of C and so on. So we deflate. We call this deflation. So each time we deflate the matrix, and then by deflation, we find a smaller matrix. Once we find a smaller matrix, what is the strategy? We apply the power method to a smaller matrix. Then smaller matrix has the biggest eigenvector, right? Or the eigenvalue, right? Do you follow me? If you apply the power method to a smaller matrix B, take a look. So this is the strategy portion, not the theory portion, but strategy is this. We have a matrix A, and then we find a similar matrix having biggest eigenvalue here, and then zeros here, and then smaller size matrix here. So this is the strategy. So we have an A matrix and then B matrix. Then A matrix has this biggest eigenvalue and then unknown eigenvalue. Now we deflate. Then these are similar. Then the eigenvalue here is lambda B, and then eigenvalues of B, right? Eigenvalues of B. Then how can you find the eigenvalues of B? Eigenvalues of B can be found by power method, right? Power method determines the eigenvector corresponding to the biggest eigenvalue of B. Because already the biggest one was extracted when we detach the unnecessary portion. The second biggest can be found, right? By this deflation. And then one more deflation will give a third biggest, and then one more deflation gives us whole sense of, right? So this is a strategy. In other words, we want to deflate the matrix. So this is a strategy, and if you have a question, if you question me, if you don't, then I will let you know how to deflate the given matrix. And of course, the theory behind this kind of deflation. But roughly, you should have a clear picture. We have a matrix A, biggest eigenvalue is found. Then we extract the biggest eigenvalue, and then we make smaller matrix, which has similarity like this, right? A and B, A and this whole thing are similar. Then with this matrix, the eigenvalues are this lambda B, and then eigenvalues of B. Then eigenvalues of B can be found by power method. The biggest eigenvalue can be found by the power method. And then by the power method, next to biggest, next to biggest, next to biggest after each deflation. So this is the strategy. So I will now summarize the strategy one more time. So let's call this way. A matrix becomes A2 matrix, and then A3 matrix. A4 each time is smaller, it has smaller size. So A matrix has biggest eigenvalue, A lambda 1. Then after deflation, we have smaller size matrix, right? Then we will have second biggest eigenvalue, lambda 2, by using power method to this one, right? By applying the power method. And then by applying the power method, we find the next biggest one, lambda 3. By applying the power method, lambda 4. So each time we deflate and find the biggest one, and deflate and find the biggest one, deflate, find the biggest one. So this is the situation. Why? Because the eigenvalue finding is so tough. Eigenvalue vector finding is so tough. We are doing this kind of thing. So you should have this clear picture, but if you don't know what is going on, let me know what part is tough. So if you find some nice method that can determine all eigenvalues very easy, then it would be great. You may be able to publish a paper on eigenvalue finding. Of course, eigenvalue can be found by many methods, not an exact method. Exact method is not numerical. Power method is numerical, as you saw, right? Power method is multiplying many times. It's very numerical method. But other methods are not that numerical. So one more time. Matrix A is given. Then we deflate the matrix. So then we get smaller size matrix A2. And then find the biggest eigenvalue of this A2 by power method. So we have found two different eigenvalues. And then now we deflate this thing in smaller size matrix, right? And we use the power method to find the biggest eigenvalue of this matrix. And then by using the power method, deflate, and then using the biggest and so on. So we continue this. So once you know the deflation scheme, you can handle it. Yes? That is the one that I will cover, because it requires householder matrix. I will let you know what you need to do. Theoretically, both theoretically correct, but I will cover practical way first, because in the past I derived all these things and proved all these. About the time I complete, students mostly lost the complexity of the derivation. So I will try to show you the way of finding or using this kind of householder matrix to deflate, and then later I will prove or show you the theory. No questions? Then the key idea is this. We want to keep the similarity. Similarity means we should have some matrix multiplied in front and after, but they should be the same matrix, and one should be inverse of the other, right? So we should have this product to get similarity. So once you have the similarity, the determinant of this thing, and then determinant of this thing are the same, right? Because of equality. But now, determinant of this thing and determinant of this thing are reciprocal. So we can cancel this out and determinant P is determinant Q. In addition, we can even subtract lambda times I from both, right? Lambda times I from both, and still the same, and then you can do the same thing. So theoretically it's possible, but later I will show you lambda involvement. So currently we focus on this portion. How can you find this kind of matrix called the householder matrix? So let's return back, and then this is the idea. First of all, householder matrix I introduced last time has these properties. Householder matrix satisfy these nice things, very nice things, and then to determine a house matrix, on the right-hand side, what should be determined? To determine a householder matrix, what should we determine? Here, W, right? Do you follow me? So once W is determined, we can automatically do identity minus 2 times this product to get U. So W determination is important. Then W should satisfy this condition. The true norm of W should be 1, and then W should satisfy this condition. So how can you find W is written here? W is V, and V equals V1, V2, V3, and we can determine V1, V2, V3 by following this algorithm that I introduced last time. I don't want to go through one more time, but you now have the picture, right? So by following this, you can determine V, and then you can determine W eventually, and then W determination will give you the U determination. So you can determine the householder matrix by following this algorithm. It's not very difficult to implement this algorithm. After this determination, we can determine more. How? Assume that we want to achieve this kind of thing. U times C1, C2, something, CR, right? Unchanged part, right? Fixed part. And then the part that will change, D1 up to D something. U times this column vector becomes unchanged part, and then changing part, but now all these are collapsed into L. All these are collapsed into L, and then 0. So how can you achieve this kind of matrix multiplication? Some column vector times U becomes this one. How can you achieve it? By finding V matrix, right? V matrix and W matrix. W consists of 0 vectors, unchanged number, right? The number of unchanged entries, right? Unchanged entries, and then V. So many zeros, and then V1 through V something multiplied gives us the U. So take a look. Once we determine this kind of W, then this W will determine what? U. Then once you multiply U to the column vector that you have, right? That you have, then this multiplied by U will give us this kind of thing having many zeros. So this is the target that you want to do. But if you do not understand the situation, ask me. So how can you find this W matrix, or more precise V matrix, V column vector? Follow these things, right? If you follow these things, then you can determine V1, V2, V3, V4, V5, V6, and so on, right? Follow this. Roughly, I explained the way of finding the householder matrix U by finding W. So once you determine W, you can find. And now it's time to use actual example. Last time you picked something, but I felt it's a little bit awkward to use yours. So I decided to use something that could be handled nicely. So assume that you have this situation. You want to find the matrix U, and then 1, 2, 2 equals some non-zero number, and then 0, 0. So you want to find the matrix U, which is very nice, satisfying this condition. So U matrix multiplied by this column vector equals some non-zero entry upstairs and then 0 downstairs. I want to achieve this thing with you, and this example will help you understand the idea of the usage of the algorithm that I provided. Let's do it. First of all, I will let you watch the formula and the actual calculation together. Instead of separately, I want you to look at these things simultaneously. So this is the situation. We want to find the V1, V2, V3 vector doing this thing. So the first thing is the determination of L. So take a look. What should we do? We should follow this portion. So L equals minus D1. So this is called D1, D2, D3. Do you follow me? We want to find U times D1, D2, D3 equals L times 0, 0. So we want to do this thing, right? I wrote the goal here. And then, because of this, D1 is what? 1. D2 is what? 2. D3 is 2. So it is equal to 1 multiplied by 1 plus D2 minus D1, 2 over 1 squared, and then 2 over 1 squared. Then it is negative 3. I found L. And then L is replacing this portion. L is replacing this portion. So we want to find some matrix doing this. U times 1, 2, 2 becomes negative 3, 0, 0. Any problems or difficulties? Then the next step is determining V1. V1 is what? V1 is what? W determining column vector, right? W determining column vector is here, right? So V1 is the first entry of W. So I want to determine V1. So V1 equals square root of 1/2 times 1 minus D1 over L. I wrote this. I'm just following the formula, right? I don't do any fancy things, I follow the formula. Then, as you can see, square root of 1/2, and then 1, and it becomes plus 1 1/3, the total 4/3. So it is equal to 2/3, square root of 2/3. So I found V1. In other words, I will write W here in transposed matrix, column vector, right? So first entry is determined. This is first entry W, right? First entry of W. And then V2 will be determined. So V2 equals minus D2. D2 is what? What is D2? What is D2? 2, right? 2 over 2 times L times V1. So I wrote this thing. Then if we simplify, then it equals two and 2 are cancelled out. 2 and 2 are cancelled out. 3 and 3 are cancelled. 3 is remaining. Minus square root of 1 over square root of 6. Just simple algebra, right? You don't even have to worry about your computer programming language, your package can handle this kind of calculation automatically. V3 is the same, right? V3 is the same, minus 2 over 2 times negative 3 multiplied by 2/3. So we have determined all the entries of W. We have determined all the entries of W. So let's go up and then write. W is nothing but this thing transpose, right? This thing transposes W. Do you follow me? Then let's finish it. W equals then I want to check whether the 2 norm of this thing is 1. So 2 norm is squaring individual things and then adding, right? Squaring individual things and then adding. Then it is, this is 1/3, right? 1/3 and the 2/3, 1, right? So 2 norm is 1. I will replace these. So I determine the W vector. Now I will determine U. And then I will show you U multiplied by 1, 2, 2 is really negative 3, 0, 0. So let's find the next thing. That is W times W star. W multiplied W star. W star is nothing but complex conjugate transpose, right? So transpose and conjugate, but it's not complex, so just transpose. So W star is 2/3, 1/6, look at the square root of this one, multiplied by transpose. 2/3, 1/6, 1/6, right? So these are multiplied together. Then this multiplied with this gives us 2/3. This multiplied with this gives us 1/3 and 1/3. And then this multiplied with 1/3, 1/6, 1/6, 6, 6. Then U is almost determined because the subtraction part is completely determined. Then it's time to determine U. Take a look. U is what? By this, U is what? 2 times this product subtracted, right? So U equals identity 1, 0, 0, 0, 1, 0, 0, 0, 1 minus 2 times this thing, 4/3, 2/3, 2/3, 2/3, 1/3, 1/3, 2/3, 1/3, 1/3 subtracted. Then final step is just subtraction. So final step is just subtraction, then minus 1/3, minus 2/3, minus 2/3, and then minus 2/3, minus 2/3, and then 2/3, and then minus 1/3, minus 1/3, 2/3. So now I completely determine the matrix U. So from this point on, I will investigate it. Yes? No question? Then instead of hand calculation, I will use MATLAB. So I will define U, and then I will check all the properties. First of all, U star times U. U matrix, I will use uppercase. U matrix equals, first row is negative 1/3, negative 2/3, negative 2/3, right? Negative 1/3, negative 2/3, negative 2/3, and then negative 2/3, and then negative 2/3 and negative 2. Third one is, third row is negative 2/3. 2/3, right? 2/3. So did I write the matrix correctly? So I will display, and then I save as U matrix, right? And then run it. And as you can see, this is the U matrix. Then I want to check all the properties. The house order matrix is derived by this thing, and it should satisfy transpose multiplied by itself is identity. So let's do it. U transpose multiplied by U, right? So let's check it. Identity, right? Transpose multiplied by U is an identity. And then I'm checking all the properties, right? So I derived U by using W, and then now U satisfied the first thing, now the second thing. So I will subtract U matrix from its transpose. Do you follow me? I will subtract the right hand side from the left side. Then it should be 0, right? So I will do it. So I will suppress all these things and then write the last result. If we have U transpose minus U, right? U. So I will save and run. 0, right? U transpose minus U is 0, meaning U transpose and U are the same. The next property is W. I already calculated W length, right? W length is already calculated. Now, this is the important thing. U times this D1, D2, D3 matrix, the column vector is negative 3, 0, 0, right? You should get this thing. So I will do U times the vector, column vector 1, 2, 2 in transpose, right? 1, 2, 2 transpose. It's column vector. I used to, in row vector, I attached the transpose. This should be equal to what? This should be equal to what? But because of the theory, it should be equal to what? Yeah, that is the only one to get. So let's do it. Done, right? So house order matrix is found by the algorithm, and then it is very nice. It's a very nice matrix. You don't have to worry about the inverse. Inverse is nothing but the complex conjugate y star transpose, right? Or itself, right? U inverse is itself. Why? Because U times something is I means it is inverse. Then inverse and itself are the same. You follow me? Inverse and itself are the same. In other words, in the theory of similarity, as I mentioned before, in the theory of similarity, we need to find some matrix, inverse and A. But if you use house order matrix, you don't have to worry. Just U and U multiply together, because this inverse is nothing but U. In addition, as you can see, this determinant is 1, right? U determinant is 1. Right? So we have very nice property. Do you need more examples, or this is enough to understand the house order matrix completely? So I mentioned about this nice matrix called the house order matrix. And house order matrix satisfy these conditions. And to create this one, we need W. And to create W, we follow this algorithm. And then this algorithm purely depends on this shape of this thing. Times, yeah. Yes.
What are we getting on the right side?
Something that may be nice, deflating something. Okay. Deflating the given matrix. Right. So we want to deflate the given matrix into this kind of form. from the given matrix, we want to deflate it. Then how can you deflate it? Use Householder matrix. If you use Householder matrix, A matrix or P matrix becomes some matrix of this pattern. Matrix of exactly this pattern. So if you use Householder matrix, then A matrix multiplies Householder matrix, say Q, and then Q inverse or Q inverse and Q. Then QAQ will become this type of matrix, as you can see, deflated matrix. Right, first column of A matrix. Of course, this householder matrix is generally applied. Give me a, so now, instead of using hand calculation, I will use MATLAB calculation. Then give me any column vector, then I will do whatever you want to do. That way, you will confirm whether you really understand this technique or not. Without understanding this technique, how can you program? So I will use new page, and then I will create the householder matrix for the column vector that you may choose. So I want to find the householder matrix multiplied by something, and you can determine the size. Any size is okay. What size do you want? You can name numbers. First of all, size. How many entries in this column? Only 3? That's 5, right? Let's make 5. Then how many do you want to fix, and how many do you want to remove? In other words, if you apply the householder idea, then, for instance, you have 1, 2, 3, then you can fix all these things, and then somehow compress these things. Or you can fix top 2 and compress these things, or you can fix top 1 and compress all these things. So how many do you want to fix in these 5 entries? How many do you want to fix? Excuse me? 1. Then, for instance, I will fix 1. And then these will be compressed. Do you follow me? Then you may pick any numbers in this column. What number would you like? 3, negative 2, 1, 2, 4, 5, right? So I picked this number. Then the goal is this one. I want to fix the first entry and then compress these things in one number called L, and then 0, 0, 0. This is what I want to do. Do you follow me or not? This is what I want to do. So it's not, the setup case is general. No matter what entry you have, you can fix or change as you want, right? In this case, I want to fix the top one and then change the, or you don't want to fix, sometimes the previous example, I didn't fix anything, right? I just completely compressed. So it's possible to completely compress, or it's possible to fix, for instance, 2 entries or 3 entries. Do you completely understand this situation? Or not? Householder matrix do this magic. So give me any column vector, then you can do anything that follows this kind of scheme. In other words, assume that, so I will make it more general, assume that you have a column vector like this. 1, 2, 3, negative 1, 2, 5, 7, 9, 10. Then you want to fix these many entries, but you want to compress things below, right? Then householder matrix can be found to do these things. Fixed portion, and then compressed portion, right? Compressed number, and then 0, 0, 0, 0. So householder matrix creates a lot of zeros. So you can use any column vector. But this any column vector could be found from the matrix, because matrix has first column, second column, and third column, right? So if you completely understand the situation itself or problem itself, then I will try to do this thing. But if you do not know what is going on, ask me. Then let's do it. First of all, as you can see, because of this situation, this portion is fixed, right? This portion is fixed. Then W also has the fixed portion, 0. And then the remaining portion, V1, V2, V3, V4, right? W is determined this way because the top one is fixed. So I will show you why using the explanation portion. As you can see, we are doing this thing, right? We are currently doing this thing. We want to fix R numbers, right? We want to fix R. So R numbers, as you can see, do not change. We want to fix R numbers and then compress the numbers below completely by just one number and then 0. So to do it, we should set up the matrix W by using unchanged number portion having zeros, and then the number that we need to determine. So I used 1, 0, and then V1 through V4. You follow me? Or not? So W is set this way. Then the next step is determining L. But now take a look. D1 is not top one. Top one unchanged portion used different letter C, right? Top one used C letter. So D1 starts at this point, right? So what is D1 in this case? What is D1? Negative 1 is D1. So as you can see, I will use this formula. I will just use this formula to determine it. So D1 is negative 1, D2, D3, D4. So L equals negative 1, square root of this divided by this one, then 1 plus this divided by this, 4, and then 16, and then 25. Right? So this is L. If you don't know why, I'll compress and then show you. So take a look. L is determined, right? L should be determined by this formula, D1 multiplied by negative 1, and then this. Do you agree with me, or you are lost? The next step is, of course, let's finish this calculation in MATLAB. So square root of 1 plus 4 plus 14 plus 25 is 6.78, right? 6. Of course, it's approximately, right? So our result is not exactly correct, but approximately. The next number is, I will program it instead of just writing it. So I will program this thing. It's called L, right? L equals square root of 1 plus 4 plus 16 plus 25. So I program it, and save, and then run, and I found L. L is found. The next step is finding V1. V1 is what? V1 is the first entry that should be used to determine W. Do you follow me? So I will determine V1 using this. So now I will use MATLAB instead of hand calculation. So V1 equals B is how do we determine an array or something? Just B is, let's say, 0, 0, 0, 0, and later I will convert this thing to a transpose vector. V is determined then. V1 is now square root of 1/2 multiplied by 1 minus D1. D1. So let's define D. D is equal to negative 1. D is equal to negative 1 and what? 2, 4, 5. 2, 4, 5. Do you follow me? So I define D and then v vector, and then now I am using formula to determine it. So it is equal to 1 minus d1 over L. Done, right? Any questions? Then afterwards, it is very routine. For j from 2 to 4, v of j equals, by this formula, d of j, I will use k, because I used k, d of k over 2 times L times v of 1. So I will do it. D minus d of k over 2 times L times v of 1. Done, right? I completed. Then MATLAB will find the v vector. So save it and then run it. And then I will introduce v in row form. And when you do calculate, I will use column form. So this is v. V vector is the column vector, 0.7574 negative decimal, right? So W equals, I will suppress all the intermediate results. And then I will expand this. W is what? 0 and then V. Do you follow me? The top entry was 0. So I'm writing this portion. right? 0 and then V1 through V4. It's this 0 portion. So let's run it. Then this is W. Then now I will attach this transpose and then suppress, and then now 2 times W transpose will be calculated. So this is the part that we should subtract. Then the next step is identity, right? Identity of 5, right? Size 5 minus the previous one, right? So I can even attach it, but it's okay. So this is the householder matrix U. You believe me or not? Courtly. U is found, and then now I will do U multiplied by the matrix that I created. It was what? U matrix was what? I mean, this column vector was what? 3, -1, 2, 4, 5. Right? 3, -1, 2, 4, 5 transpose, right? This should be what? This should be equal to what? 3 fixed, and then some number, and then 0, 0, 0. That was the goal. So let's check whether we really did it or not. Done. So as you can see, once you create the householder matrix, any column vector can convert to the pattern that you want, right? Any fixed amount of numbers, right? And then all the following numbers are compressed into one number, and then all the below numbers are zeros. The householder matrix is completely explained, and then I even showed you how to implement. Basic level implementation was shown. So please check your note and check whether you really follow this idea to create householder matrix from any given matrix, right? From any matrix of the right, any right side, right? This could be any column vector, anything. For anything, you can fix any number of entries, right? And then change the numbers below by compressing all these D1 through these two, some number, and then zeros. It's house order matrix idea is very important. And as you can see, implementation does not require tons of lines. A few lines can implement. So no questions about house order matrix itself, because after this, we use house order matrix idea to deflate or to do many things. The house order matrix is an essential part for the following skills. Then let's continue. With this, you are equipped with this one. And the theory part, as I mentioned before, in the past I explained these things by wasting a lot of hours. People couldn't understand or even lost. So I intentionally skip all these things and then go to the deflation. Of course, if you are interested in the theory, ask me. And I will go through these things with you, go through the skipped portion with you. How do we, in fact, deflate? How do we deflate? In other words, by the power method, we can find the biggest eigenvalue, right? Then we want to deflate. Then how do we do it? So take a look. By the power method, we have found maximum pair, right? Maximum pair, eigenvalue vector pair. Then the next step is defining. I do not like this choice, because if you star, it may look like some kind of strange symbol, but just name. It's nothing more than just name. So V1 star is just name. It's defined by this V1 divided by this one, and then how do we choose it? This V1 could be plus or minus, right? This could be plus or minus, but we should let the result of this minus. Do you follow me? Result of this V1 divided by V1 norm becomes what? Negative. The top entry is negative. That's the one you should do. Then afterwards, you find the house order matrix doing this. Some house order matrix, U matrix, right? I used the letter P. U matrix multiplied by some column vector equals this thing. So you achieve this goal. Why is it 1? Because we normalized, right? V1 is divided by its length. So it's normalized. So this is the reason. Then what happens? If we somehow find P, then P times A times P is deflated one. It will be exciting, right? So this is the situation, and then we will follow these steps to do it. So instead of using arbitrary one, I will use the homework one so that you can be familiar. Oh, mistake. I will open another tab instead of. So homework one might be a nice one that we can use as an exercise. So I will use this one, and I will show you how I deflate, especially what matrix is required to be deflated. There is a deflate A, right? A. So I will use the top matrix. So let's make this window small, and let's open the So I will write it. So these might be necessary in the future, so I will just read it. And the A matrix is 3, negative 2, 0, 0, and negative 2, 5, negative 3, 0. Zero, negative 3, 7, negative 4. 0, 0, negative 4, 9. So I defined A matrix. Any questions? So I defined A matrix. Then it's not necessary anymore. Then, the idea part is necessary. So I will show you the idea and follow the idea one more time with you. So what is going on? first of all, with A matrix, find the maximum pair, maximum eigenvector value pair by one method, power method. So I will show you the power method one more time. So I will go up and then show you power method. The power method is right here. This is the power method. Right? This is A matrix times X and so on, right? So let's suppress all these things. How do we suppress all chunk? Do you know how to suppress the chunk? Thank you. Thank you. Thank you. So A is done. Now X is what? 1, 1, 1, 1 column vector, right? So I defined A, and then I defined X. Then, as you can see, A is given. Now X is initialized. I used 1, 1, 1, 1, right? And then Y will be determined. So Y equals A times X. And then next step is B. So B is the maximum entry of matrix column vector Y. Or I do not remember. Maximum component of Y, right? Maximum component of Y. Right. And then, now X is what? X is Y over B. Y over B. Right? So I should loop it, right? I should loop it. So let's loop about 6 times. 4. I running from, K running from 1 to, initially 3 times. So do you follow me or not? I'm just using the power rule, power method. Then save it, and then run it. Then as you can see, take a look. Initially, this is A matrix, and then this is X matrix, and then X matrix times A matrix gave us Y matrix. And then Y matrix maximum entry is 5, right? 5 divides A matrix, I mean X, Y matrix, Y column vector, so we get this, right? And then this is multiplied by A matrix gives us this Y, new Y matrix, Y column vector. And then the maximum value is 9. And then 9 divides everything, then we get this thing, right? We get this thing. And then this thing multiplied by A gives us this thing Y. And so, right? So we continue these things, and then we get these things. So let's increase the number of iteration, and then let's suppress intermediate results. Let's suppress these intermediate results. Then what happens? Then, as you can see, Y is what? This thing, right? Y is this thing. So this is the maximum X is this thing, right? So eigenvector value, if you divide by a constant, you do not. Vector, eigenvector. We are searching for an eigenvector, right? Right. Biggest eigenvector. Biggest means eigenvector corresponding to the biggest eigenvector. Just a moment. What is your question? Oh, of course, we will find eigenvalue, but to check whether it's an eigenvalue or vector, I will do this thing. What is A times X? I will do this thing, right? A times X is what? This thing. Then we want to find the eigenvalue, then R can be introduced, right? R can be introduced. 1, 1, 1, 1. Do you follow me? 1, 1, 1, 1 is introduced. Then how can you find the eigenvalue from eigenvector? R multiplied by A multiplied by X over R multiplied by X. Do you follow me? We made numbers. number of number is possible. Thank you. Thank you. Do you follow me? So this is the way to find the eigen value from eigenvector. Because eigen now vector is x, right? Eigenvector is x. We can find the eigenvalue. So this is the formula that I provided, right? So let's find it. Then we will find the eigenvalue. Because of this 12, this is eigenvalue. So let's store this thing. Let's store this thing at some place. So I will store this thing. Here. So this is called eigenvalue. So I say eigenvalue 1, right? Eigenvalue 1 is this one. So now I save and then run, and then we will find eigenvalue E1. E1 is found. So let's check whether it's really an eigenvalue or not. So to do it, A multiplied by x minus E1 multiplied by x. E1 multiplied by x will work or not? Size-wise, 1 by E1 is 1 by 1. Will it work? Let's check it. Before ask, let's ask. Does not work. Oh, it works, right? This is very small. And result, the error is very small. But still, I do not confirm E1 times x is what we expect. Still okay. So the error is very small. In other words, it's an eigenvalue vector, right? Do you follow me or not? Now, by power method, I found an eigenvector x. And then I also found eigenvalue. So let's call this V1. So let's call this x. Maybe to have a better result, we can do the iteration more, right? More. So I iterate this more times and then run it. In any case, this is found. E1 is found. And then the next thing is this. We want to, I go to the theory part. We should now, so this V1 is found, right? V1 is found. Then the 2 norm of V1 should be calculated, right? 2 norm of V1 should be calculated, and 2 norm of V1 divides V1. So V1 norm is equal to norm of x 2 norm, right? So let's run it. Norm is 2 norm is 1.4. Is it that small? Could be, right? 1.4 is the norm of x. Then this should divide x matrix. X is divided by V1 norm. Is called V star, right? V star. So let's do it. So V star is found. V star is found. And then is the first entry negative or positive? What was the requirement? What was the requirement? We determine V star, V1 star, and then first entry of V1 star should be what? Negative. So we satisfy. If this is not negative, then you multiply by negative 1, right? You multiply the whole column vector by negative 1. And automatically, so it's not very difficult to get a negative, right? So V1 star is found. Then, now what should we do? V1 star is found, then this V1 star becomes what? Now we are using this. V1 star is, we are using these things that we created, right? Do you follow me? Oh, I should have used automatic one, right? Uncommenting it, but almost there. So do you follow me? So now I should have used this upstairs. So we used this situation, and then D is nothing but B1 star transpose, right? B1 star is a column vector, right? B1 is a column vector, so B1 star transpose is D. And then D is nothing but the L is nothing but, because it's minus is plus, right? So 1, right? Because it is divided by its norm, right? L is square root of those things, and this is the norm, right? Square root of the norm is norm. The norm is 1. Then, how many entries do we need? The size is 4 by 4, right? Everything is the same afterwards, right? Everything is the same. Then we will find this thing, right? And then we can check whether it is deflated or not. So A times U. So I roughly completed everything, and then it's time to run. 34. What is the problem? Do you find any problem? Oh, it was, I solved a different one, right? V is W. I solved the previous one, right? So this is the change. Done, right? So take a look. Is it deflated? A was a given matrix, 4 by 4. But now, after finding U matrix, biggest eigen value is extracted, and this have zeros. In other words, now we have this portion called, let's say, A2, right? So now, let's call this result, right? Result is this one, and then now deflated, right? So A2 equals this result matrix to cut from second row to the end, right? And then second row to the end. So I display both. So as you can see, we have a matrix A, then by the steps that I mentioned, I deflated. After the deflation, I extracted smaller size matrix, then apply power method to this matrix. So if you apply power method to this matrix, what do you get? You will get the result. Then you can loop, right? So you call this A matrix, right? You call this A matrix, and then you go up. Right? You call this A matrix, and then you go up, and then follow everything, right? Follow everything down. But as you can see, if you hardwire the length, then you will be in trouble. So it's good to use length command, right? It's good to use length command instead of hardwired fixed numbers, such as, for instance, 2 to 4. You should not hardwire this thing. You should use length command to automate this, and then looping will automatically deflate and find the smaller size matrix, and then deflate, and then it will automatically do it. Do you follow me? Completely follow me or not? I will show you one more time. Take a look. A matrix is given. Then power method is applied. To use power method, I just initialized and then multiply many times, and then I got the result x, right? Result x or y. Both are okay. X or y are okay, because once it's an eigenvector, then multiplying by A will also an eigenvector, right? The same. So we got the result, and then result determines eigenvalue too. So eigenvalue vector pair are found, right? Eigenvector value pair are found. Then we can find the norm of this eigenvector and then divide it by the norm. And then we now hold this D matrix, a D column vector, and then because we divide x by its norm, the L will be 1. L is nothing but the norm, right? Norm with signed norm, right? So signed norm is L. And then afterwards, we use the determination of V1 through Vk or Vn to determine W column vector. W column vectors are used to determine household matrix U. Then once you determine U, U multiplied by A multiplied by U will deflate. So we can do the deflation of the matrix, and then eventually, as you can see, A matrix is deflated. A matrix is deflated to this one. So given matrix became this thing. And as you can see, deflation means eigenvalue here and then 0, 0 here. Then the eigenvalue of the given matrix and the eigenvalue of this should be the same. Then if you subtract lambda from the main diagonal, this minus lambda will be separated. Then this whole thing result and the eigenvalue result of A should match. That means this eigenvalue will be the same as the eigenvalue of the given matrix A. So we now focus on smaller size matrix. We do the same thing over and over again to deflate, and then eventually we'll get all the eigenvalues like these. Then by the inverse iteration, we can find eigenvalue. Next time, I will show you the method of finding eigenvectors from values by using inverse iteration, which is the disguised form of power method.